Hello, I am Professor N.B. Hulle from G.H. Raisoni Institute of Engineering and Technology. In this video, we will calculate current in the 2 ohm resistance by using the Norton's theorem. Now here we will apply the steps of the Norton's theorem. The first step for the Norton's theorem is remove the load resistance and short the output terminals and calculate the current in the short circuit, which is nothing but the Norton's current. For this case, if we are doing that, then figure will be something like this. We are removing the load resistance and shorting the output terminals. Here it is 6 amperes, 24 amperes, and if we are shorting the output terminals, the current in the short circuit is nothing but Norton's current. Here it is 4 ohm, this is the 6 ohm, and here whatever the current we have, that current will be the Norton's current. It is A terminal, B terminal. Now here in this case, for the calculation of the current, second step is the calculation of the Norton's current. Now for the calculation of the Norton's current, we should not use the nodal analysis, because again in this case between the node A and B, this path is the branch and this branch has 0 resistance. Whenever there is a path having 0 resistance, try to avoid the use of the nodal analysis method. Now here in this case we cannot use the direct inspection method, because in that case we don't have the procedure for the current source. The one way is that we can convert this current source to the voltage source, this current source to the voltage source, figure will become single loop. We can work out its current and single loop, that will be the Norton's current. But here I will use the mesh analysis. Now here this is the first loop or first mesh, its current is I1. This is the second mesh, its current is I2. And this is the third loop, its current is I2. Now here I am assuming the direction of this loop, which is very same as direction of the loop current, which is very same as the direction of this current source, to avoid the taking of the minus sign. While using that, we have to be little careful. Now here in this case, from this figure directly we can have this I1 is equal to first current, which is 24 amperes, equation number 1, and from the loop number 3 we have this I2 is equal to 6 amperes. This is equation number 2. From this loop we have, this is 6. From this we have I1 is equal to 24. If we are taking its direction as a clockwise, in that case this I2 will be opposite to that of the 6 amperes. That's why its value must be the minus 6. This sign should be the minus 6 if we are taking it as clockwise. But I have taken it as anti-clockwise. No issues. Now here we should have a third equation. For that purpose we are applying the KVL and we are traveling from this corner into the loop in the clockwise direction. Before that we will mark the terminals. This is clockwise current I1. This will be the plus minus. This is clockwise current again. Plus minus clockwise. Positive negative and so on. This is anti-clockwise. This will be the plus terminal. This is minus. And if we are applying the KVL to the loop number 2, we can have an equation something like this. If we are traveling from this point, positive to negative, which is minus, its resistance is 4 and its current is IN minus I1. Because IN is upward, I1 is downward, we are following the sign conventions of the I1. That's why I1 is opposite to that of the I1. That's why it is minus sign. Then if we are traveling something like this, positive to negative, which is minus, its resistance is 6. We are following the sign conventions of the I1. Now look at I1 is downward, I2 is also downward. That's why the resultant current must be IN plus I2. In this case, it is downward, it is downward. That's why its value will be, that is IN plus I1, which is both are downward. And then there is no element in the circuit, which is equal to 0. This is minus 4 into IN, minus of minus 4 into I1. Then it is minus 6 IN. Then minus, it is 6 into I2, which is equal to 0. Now here, if we are substituting the values of the I1 and I2, then we will get, this is minus 4 into IN plus 4 into I1, and I1 is 24. Then minus 6 into IN, then minus 6 into IN, then minus, it is 6 into I2, and the value of the I2 is 6, which is equal to 0. If we are simplifying further, this minus 6 IN and this minus 4 IN, we will shift on the next side, which is equal to this 6 plus 4, that is 10 IN. This 10 IN. On the left hand side, this is 24 into 4. This 24 into 4, its value is equal to 96. This is 96. Means here it is 96 minus 36. This is minus 36. 60. This 60 divided by 10 will be the IN, which is 6 amperes. Now we know the IN, that is current in the short circuit, which is Norton's current. Now here we can calculate the Norton's resistance as per the step number 3. We will use the step 3 for the calculation of the Norton's equivalent resistance. Now here, if I am using the step number 3 here, I will draw figure first. Here this is terminal A and this is terminal B, and this load must be replaced. How we will calculate the Rn? Rn is the Norton's equivalent resistance calculated at the output terminals. When the load resistance is removed, this load should be removed, and all sources are replaced by the respective internal resistances. This is current source, this is voltage, current source again, and current sources has internal resistance of the infinite. That's why this current sources should be replaced by the open circuit. This figure will become something like this. Here is 4 ohm and this is 6 ohm. This is A, this is B, 6 ohm, this is 4 ohm. This current source is replaced by infinite. This current source which is available here is replaced by the infinite. Means terminals are removed, or terminals are kept open in the air because air has the infinite resistance. Similarly, this current source is also replaced by the infinite resistance. Now, whatever here we have the resistance, that resistance is Rn. Means here, in this case, Norton's equivalent resistance, which is equal to 6 plus 4, that is 10 ohm. Now here, we have the two values. We know the Norton's current. We know the Norton's equivalent resistance. Then we can draw the Norton's equivalent network in the step number 4. This is the step number 4, and we can have Norton's equivalent network, which is something like this. And the load resistance will be connected between the terminal A and B, which is removed in the step number 1. This is 2 ohm. This Rn is 10 ohm, and this IN, that is Norton's current, is 6 amperes. We are interested in the calculation of current in this branch, which is IL. Now, this IL will be total current 6 amperes. I am using the current division rule. This is 6 amperes total current. Current in this branch is known. We want to calculate current in this branch. That's why opposite branch total current into total current into resistance of the opposite branch, which is 10 divided by resistance of both branches, that is 10 plus 2. 10 plus 2, which is equal to 60 divided by 12. And here the final answer is it is 60 divided by 12, which is equal to 5 amperes. This 5 amperes is the current flowing through load resistance by using Norton's theorem in this particular case. That's all for this video. In the next lecture, we will try to understand the basics about star and delta conversions. And then I will solve some problems on Thevenin's theorem, where the calculation of RTH will be based on star and delta conversion, and the calculation of Rn, that is Norton's equivalent resistance, will be based on the star and delta conversions. That's all for this video. Thank you.